They are not trick questions. They are things actually, something we've already discussed in here, but we did not apply it to the context of chemical equations we're doing now, but these are answers you should know based on some stuff we did back when we were looking at combustion analysis and percent compositions and empirical formulas. So I'll give you about a minute here. Get them locked in. Again, they're not trick questions. And I'll see if I can find the page reference or the note reference of when we went through them. So let's see, probably back around the 17th. No, might have been before the 17th. Let's try the 15th. Would have been before the 15th. Maybe the 13th.
Should be page 133.
Okay. I'm looking for a reference that we did in class, though. Here's the 10th. Yeah, wow, it's before then even. So it would have been maybe on the 8th. Here we go. So here's our reference. Back on February 8th, we talked about combustion of compounds. And if we burn a compound containing carbon, it's going to produce carbon dioxide. We burn a compound that contains hydrogen, it will produce water. And if it contains sulfur, it's going to produce sulfur dioxide. So all three of our examples contained which two elements? All three of them there on the Socrative contain which two elements? Carbon and hydrogen, which means assuming complete combustion, we'll always see products of carbon dioxide and water. Okay, so today we're going to look at a couple of examples. Let's go ahead and do the one of them there that was on your Socrative app, and then we're going to come back and look at this one here that a number of us had trouble with the other day. So we do a very simple one, and I guess I just put this away. There's a reason why I had it out. Anybody know the primary component of natural gas? Oh, that was in your Socrative. What is it? I know, it's 2 minutes ago. Easy to forget. What is it? Primary component of natural gas is? Methane. Methane. Primary component of natural gas is methane. And by the way, methane is colorless and odorless. And so nobody knows if you're a methane producer, because even if you fart or whatever, fart is not, the odor is not caused by methane, it's caused by sulfur compounds that you are emitting. So methane itself is colorless and odorless. So when you smell natural gas, what is it you're smelling? It's not actually sulfur, but a sulfur compound. And why do we add a sulfur compound to natural gas?
Because methane can kill yourself.
Yeah, so we can tell that there's a leak because it's an explosive gas. So that's where the odor comes from. But methane itself is colorless and odorless. So let's go ahead now and write out a chemical equation for this reaction, assuming that this is methane gas exclusively. So to do this, methane has a formula of CH4. We are burning it, which means we are reacting it with oxygen, which has a formula of O2. And again, the products would be CO2 and H2O. At this point, once we determine, and by the way, why am I writing H2O as a gas? Because what phase is it being produced in here? Producing as a gas. It's at a high temperature. We don't see liquid water forming all over here. So now we want to balance this chemical equation. How many carbons on each side? 1. How many hydrogens on the left? 4. How many on the right? So what do we need here? A 2. That balances the carbons and hydrogens. The only thing we need left to do is to balance the oxygens. And we'd balance the oxygens by putting 2 right here in front of the O2. Any questions on this one here? Okay, one of the other ones that was in your Socrative app to begin with today was this one. And I need my safety glasses for this one. And I also need to kind of clear this area off of here. And we'll pull this away. And we're going to take some methanol and we're going to put it in this 2-liter pop bottle. And we'll go ahead and close this off. Set it aside. And we'll go ahead and shake this up a bit. Volatilize the methanol. Pop this off of here. Of course, now this is one that's a lot more fun to do in the dark. And just in case we have an issue, we'll put up an explosion screen. And we'll turn the lights down here a little more. And I need my tongs here. So we'll go ahead and light the flaming splint. And if we pop it in, we see a reaction. And of course I like this one because of course it melts down and everything. And then I often hear, let's see this again. Now I actually used to do this with a much larger container. I used to do it with a big water cooler carboy. However, it's turned out that this is one reaction that the American Chemical Society now has even taken a position on as being one that we got to look after some safety issues for. And so I use a much smaller container now, and it's one of a softer plastic, so generally if it would explode it's not going to send out any big plastic shards or anything like that. So on this one here now, if I go ahead and light it and test it again and we watch what happens, notice that the only place we're seeing a reaction, I don't know if you can even see it, is where? The very top. And the reason why we're seeing this at the top is because, I'm going to close this off. What happened the first time?
CO2 in the water.
Yeah, we produced carbon dioxide and water. And what did we get rid of the first time? What was in here before? Well, what were the reactions?
Oxygen.
Yeah, we got rid of the oxygen. So the oxygen was gone because that reacted the first time. We replaced it with carbon dioxide and water. So the only place it was burning this time was at the top because the oxygen was up here. The oxygen was not down here on the inside. So again, I'd like to show this. I've had some fun with this one over the years. In fact, up here you'll see, you know, we have a camera up on the ceiling here, and on that camera, back in the early 2000s, I used to, instead of writing on a tablet PC, I would write on a document camera up above. And when I had the big carboy exploded, and the methanol went all over the top, and it caught my notes on fire. So anyhow, right here, these are my notes. And so threw them in the garbage, had one of my colleagues hear the story, and then they retrieved the notes out of my garbage and then presented with me, and oops, I set my notes on fire award. But oh, and then there was another one that I did back, this is my first year of teaching, back, I taught high school down in Waseca, if any of you know where that is. In my very first year of teaching, if you look at these light bulbs up here, these are 4 feet long. And if you go down to the gymnasium, you're going to see that these fluorescent bulbs are actually 8 feet long. If you go down to the gymnasium, though, you don't want basketballs and volleyballs and stuff hitting the ceiling. So what they do is there's a clear plastic tube that goes over them. And so I went and retrieved one of these 8-foot plastic tubes, stoppered up one of them, one end, and then I mixed up the methanol in there, and then I dropped a match down on the top. Beautiful reaction. You see this flaming, ooh, just down the 8-foot tube. But it started vibrating like that, shook the stopper out, and then of course the methanol spread over the floor. If you can believe, a carpeted chemistry floor, spread out on the carpeted chemistry floor, and the carpet caught on fire. And so we had fun with that one. But anyhow, because of the safety laws, not laws so much, but safety recommendations of the American Chemical Society, I am now stuck with a little container like this, and I'm so sorry, because the big one is so much more fun to do. But that said, we should be able to write out a chemical equation for this reaction. And if you notice the flame, what color was that flame? Blue. And what do we know about a blue flame? It's a hot flame, exactly. And so ethanol, which is different than methanol. This is methanol in here. Methanol is a 1-carbon alcohol. Ethanol is a 2-carbon alcohol. And rubbing alcohol, which is isopropyl alcohol, is a 3-carbon alcohol. But they're all very similar, and if you are involved or aware of the fuel industry at all, they'll talk about oxygenated fuel. And so when you talk about oxygenated fuel, it's fuel to which you've added a small amount of oxygen-containing compounds. So in this case, if methanol is used, and methanol is what is often used if you go down to South America, like Brazil, we would then take methanol, which is CH3OH, react that with oxygen, like we did, and burn it, and we'd wind up producing, what are the products?
CO2.
I know, really exciting, isn't it? So now once we get this, we can go ahead and balance this chemical equation. This one's a little bit more difficult, so we'll walk you through this quickly. How many carbons on each side? We got 1. How many hydrogens here? 2. And over here? Oops, we have 4 here. And on the right side, 2. So to balance this equation, we would put 2 in front of the H2O. So now we've balanced the carbons, we've balanced the hydrogens. The only thing left to balance is the oxygen. So a quick check on the oxygens. We have how many in the first formula? 1. And how many in the second formula? How many in the third formula? And how many in the fourth formula? Okay, so now we want to put some coefficient x in front of here that we don't know what it is. Of course, we don't usually write x2, we write it as 2x. So what we know then is that 1 plus 2x is equal to 2 plus 2. Of course, then on the right side, this gives us 4. This gives us 2x plus 1. We then subtract 1 from each side. We get 2x is equal to 3. We then divide each side by 2. We find out that x is equal to 3 halves. So if we put 3 halves in here, this should balance it, because now 3 halves times 2 gives us 3, and 3 plus 1, of course, gives us 4, which balances the hydrogen or oxygens on the other side. Of course, we can't leave a fraction in here, so we take this entire equation and multiply it by a factor of 2. So we distribute that 2 across the quantity there in parentheses, and we get 2, 3, 2, 4 as our coefficients. So any questions with this one? Okay, another quick blurb on methanol, which is the stuff in here. Methanol is also marketed in a product called heat, H-E-E-T. Anybody know what heat is? Oh, well, maybe none of us use it anymore, and if you don't, that's a good thing. Heat is what's used in gas line antifreeze. Gas line antifreeze. And by gas line, we're talking about your fuel line in your car. If you go into like a supermarket or a Holiday, you're going to see that they're lined up. They'll have both heat and isoheat in there. Heat is methanol, it's pure methanol. And if you get isoheat, that's pure isopropyl alcohol. And if you buy it and put it in your car in the state of Minnesota, you are just wasting money. And the reason why you're wasting money is because in Minnesota, by law, your gasoline has to contain 10% ethanol. It has to contain 10% ethanol. And if we remember, again, methanol is a 1-carbon alcohol, ethanol is a 2-carbon alcohol, isopropyl alcohol is a 3-carbon alcohol. They all do the same thing. And the function of the fuel line antifreeze is to basically solubilize, if that's such a word, to solubilize the water in the gas line. Because of course water and gasoline don't mix. They don't mix. And so what happens often in the winters in Minnesota, or what used to happen is that when it got really cold, condensate, just like condensation will form on your windows in your house on a cold day. What will happen in the gas tank is that condensation will form on the inside of the gas tank. That condensation then will go on the gas tank and will go to the bottom of the gas tank. And you know where the fuel line comes out of the gas tank? Very bottom. And because water is more dense than gasoline, the water would then go into the bottom of the gas tank. And once you got in there, if it's a really cold day, what's going to happen to the water? It's going to freeze up, and that would block the fuel line, prevent it from going through. So then what you would do is you'd add some of this heat or isoheat, which is basically alcohol. And alcohol is a substance that is both soluble in water and in gasoline. And as a result, then that would solubilize the water and allow the water and the gasoline to mix together, and they could get carried through. But today you don't need it because your gasoline by law already contains 10% ethanol. And so the ethanol that's already in your gasoline is doing that job, and in the state of Minnesota you should not be having any trouble with your gas line freezing up unless you're driving a diesel or you're driving a old-time specialty car, which you have to put non-ethanol based gasoline into it. So that's my little pitch. Any questions?
So would that be aqueous then, the phase label?
Phase label. If you're burning it, it's going to be, well, like the methanol I put in there was pure, so that's going to be a liquid.
Okay.
Yep. And then the rest, of course, is going to be gases. Anybody else? Okay, then let's go back to the one that we ended the hour with. I had a couple people come into my office to talk about this one, and as I recall, the majority of us actually got this one wrong, and there's only 50-50 chance. That means we're probably still not understanding this as a class. So we want to determine oxidizing agent and reducing agent. We had a handout the other day. Anybody need that handout from last class? Okay. All right, so now we want to determine the oxidation numbers. And we'll look very quickly. I'm going to put in a periodic table here for this, and then I'm also going to go back to last class and pull out this sheet right here. So we will copy this and we will paste it to today's notes. There we go. Yeah, I think we can work with that. Well, that's not the one I really wanted. I want the other one. So let's go and get the other sheet. Right here. Here we go. This is the one I want. We'll copy this and we'll paste it to today's notes. There we go. All right. So now what we want to do is we want to determine the oxidation numbers. What is the oxidation number on barium? 0. And which rule are we looking at? The very first one. This is an element. That's all it is. And the oxidation number of an element is 0. What is the oxidation number on the bromine? 0. And that's because bromine is an element. And remember that the oxidation numbers have to sum to be 0 on each one of these. So 0 sums to 0, 0 sums to 0. But now we're going to barium bromide. This is part of a compound. So we then go to rule number 2, which says that the oxidation number of an atom in a monoatomic ion equals the charge on the ion. So which ions are present in barium bromide? We have barium ions and bromide ions. What is the charge on a barium ion? 2 plus, right here. So we come back and assign an oxidation number. Remember, oxidation numbers, the sign goes where? In the front. And what is the oxidation number on the bromine? -1. Again, that's because the sum of the oxidation numbers must sum to be 0. So we have 2 with the -1, which gives us -2, plus 2 gives us 0. So then what we do is we pair up the like atoms on each side. Barium pairs up with barium, bromine pairs up with bromine. Bromine pairs up with bromine. There we go. So then, my recommendation is always to first check out which element gets reduced. And the one that gets reduced is the one that experiences a reduction in the value of the oxidation number. So which one got reduced? Barium or bromine? Bromine. Bromine was reduced. And it was reduced because it went from a 0 down to a -1. That's what reduction means. The value gets smaller. And the barium then must have been oxidized. Now, of course, the other way to tell that what happens here is that if an element loses electrons, it is said to be oxidized. So if it loses electrons, it must be oxidized. And from barium to go from a 0 to a +2, it has to lose electrons. It's a metal. And metals will lose electrons, and that's what happens to get to a +2 oxidation number. So once we do that, if bromine was reduced, that means it is a part of the oxidizing agent. And if barium was oxidized, that means it is a part of the reducing agent. And so here, when we list them, we would say, we'd write the whole formula. We talk about the agent, we're talking about the entire formula for that species. We talk about the elements getting oxidized or reduced, we're talking about individual atoms of the element that get oxidized or reduced. When we're talking about the oxidizing agent, we're talking about the entire formula that you see present here in the reaction. So, any questions on this one? Wonderful. Because you guys are so smart, I know. We're going to have a test in here on, what is it, Friday. We're going to have a test. And we're going to spend the rest of the hour today reviewing. And this review is going to be on your own or with your friends or partners, neighbors, whatever in here. Just as a reminder of what's going to be on the test, in your syllabus there is a section labeled there that tells you what will be on Chapter 2. I believe it begins with the mole concept, and then we went on to things like percent composition and writing out empirical formulas and molecular formulas and such. We went a little further dealing with stoichiometry, limiting reactants, theoretical yields, molarity, dilutions, and such, and then we wrapped up with our chemical equations. Now, I don't really give study guides. It's about as close to a study guide as you'll get. We don't always have time to practice in here before an exam. The happens to be an exception this semester. So go ahead. As far as what will be on the test to be provided for you, you will have your periodic table and conversion sheet. And sometimes one of the things people forget in here is that if you look on the back of your conversion sheet, looks like fourth from the bottom on the conversion side is a value that some of us forget. Even if you have it tattooed on your forehead, you don't have a mirror in here. It is Avogadro's number. So it is on here. Any questions? All right.
Will we be able to use the solubility and the oxidation
Oh.
sheets for the exam?
Not the oxidation, solubility. This will also be provided, your solubility tables. The oxidation sheet won't be because that should be common sense. Okay, the oxidation states. By the way, the other question came up in my office, what's the difference between oxidation numbers and oxidation states? Nothing. Okay, I learned them as oxidation numbers. You have to reverse them as oxidation states. They're the same thing. Okay. But if anybody was gone on the day we did solubility tables, I have some of those. All right. More periodic tables and strategies for balancing equations. Anybody need these handouts? Leftovers get recycled, and then it's a waste of paper. All right, have fun. Here, work hard on these. As far as number of questions on the tab, we should have talked about. You can start early. I think we started 10 minutes early last time, right? No seating chart this time because we have less than 38 people. So every other seat, that's just the only thing. So no seating chart, just every other seat. We're now down to less than 38 people in here. And so there's enough to go every other seat. 10 minutes early.